I'm going to change the numbering just a little bit to expand this, and so this is going to be 44.2. I'm going to rewrite this rather than b, it's going to be 44.2. We're going to discuss the infinite numbers. Infinite numbers are kind of unusual. And of course, we went for a long time thinking there was one infinity. People didn't really accept infinity in mathematics for a long time until finally it became defined as that number which is greater than any number that you could write down. And therefore, its infinity is that number such that it's greater than any number n. So you pick a number n, and infinity is a number that's greater than that. So it's defined by a condition. So you say, well, I understand infinity. It's the limit of a sequence that never stops of counting and so forth. You can also imagine that we could go to positive infinity. We could go to negative infinity. But now, what was really remarkable is the work of Cantor, who taught us a new way of thinking about number. If you think about infinite numbers, then in fact, you end up with all kinds of dilemmas that you're faced with. For example, if you take all of the numbers and you take an infinite number of numbers away, you can still end up with an infinite number. How is that? Well, you take all of the integers, let's say all the positive integers. Now subtract every even integer. Well, you're left with all the odd integers, but you still have an infinite number. Now I can take away all those that are divisible by 3. And I've taken away an infinite number, but I still have an infinite number. So I can keep doing that and keep doing that. And so infinite numbers have a bizarre behavior. It was Cantor who explained how we should rethink that. We shouldn't think of an infinity as achievable by a counting process, but rather by a comparison concept with a one-to-one matching. If we have two sets, we say, oh, there's the same number of sheep over here and sheep over here. Well, we count these sheep. 1, 2, 3, 4. And we get to 4. We count these sheep. 1, 2, 3, 4, 5. Say, no, there's one more sheep over here than there is over here. But we can't do that with infinite sets. If we have an infinite number over here and an infinite number of things here, then in fact we can't even do the counting. We just end up with infinity. So nothing makes sense. Cantor was the one that said there's another way to think about the comparison of two sets. We can think about the comparison of two sets as having a correspondence between each of the elements. So for every sheep over here, we make a corresponding sheep over here. Then he made that's his first brilliant assessment, to say two numbers are equal if I can make a 1-to-1 correspondence. I do not try to count the two sets and make them correspond to the numbers, but I make them correspond directly to each other. And his second innovation was to say, well, there are ways to make them correspond so that you've got things left over here, you've got things left over here. But if, and this was his big assertion, if there exists one way, and this is the symbol for there exists, if there exists a method such that there's a one-to-one correspondence that uses up all of the numbers in both sets, then they are the same number. Now that's kind of stunning if we think about numbers. It's kind of normal to think about regular numbers. If I can match the sheep in this pasture with the sheep in this pasture, and there's a link between each one, uniquely, a one-to-one correspondence, often called an isomorphism, then it makes sense that you've got the same number of sheep. But he's saying do that with your infinite numbers. Now let me show you how strange that can be. I'm going to take two sets. And over here, I'm going to put all the numbers. 1, 2, 3, 0 even, 4, 5, 6. And over here, I'm only going to put the even numbers. 0, 2, 4, 6, 8, da, da, da. Which is the larger set? Well, you immediately say, I've left out an infinite number of numbers over here. Therefore, this is infinitely bigger. No, it's not. They're both infinite sets. Cantor would say, these are the same infinity. How can I do that? It's the same infinity because for every number here, I can use the process of making it correspond to 2 times as much over here. So 2 times 3 corresponds to 6. 2 times 4 corresponds to 8. 2 times 2 corresponds to 4. So using the operation 2x, every number here corresponds to exactly one number here. No more, no less. Therefore, I have a one-to-one correspondence or an isomorphism. Therefore, they have the same infinity. Brilliant. Then he was able to say, these 2 infinite sets are the same infinity. Well, not all infinities are the same. Because he went on from that to say, let's look, that turns out to be the same as the infinity of the rational numbers, in fact, which you can show. But now if I look at the real numbers, this is a higher order infinity. These are the numbers that would be for the points like 2.376, da 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 da, or a number like the going to infinity, or a square root. And this turns out that there is no way to make a correspondence between the real numbers and the integers. Therefore, the real numbers constitute a higher order of infinity. If I think of that then, this is one infinity. It's called Aleph 1. This is Aleph 2. Then there's another order of infinity that's even higher, and it is the infinity of all functions. So if I imagine the real line here, and I look at functions, all of the functions f of x, where this is x, that are possible are greater than the number of real numbers. You can kind of see that because at each point, which is a real number, I have an infinite number of numbers that I can assign to that, and I can do that an infinite number of times. So this is sometimes called Aleph 3. I don't know how to write the Arabic symbol for Aleph, but assume that I've done that here. And here are 3 different types of infinities. So it's just a neat thing to understand that there are different types of infinities. Now, for those of you who are real curious, you might think, oh, wait a minute, the real numbers, this is for the real line. What about the plane? Let's back up here and look at the plane. The plane needs 2 numbers, x and y. These are 2 real numbers, so all the numbers here correspond to all the numbers here. The numbers in the plane must be a bigger order of infinity than a real number itself. No, they're not. How is that possible? Well, I'm going to show you a rule in which all the points in the plane can be mapped exactly to the points on a real line. For every point here, there's one point here. How is that possible? Well, I want to represent this point by its pair of coordinates. The pair of coordinates x, y might be something like 23.2156 da 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 for x, and 0.15132 da 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 for y. So there's our x and y. Now I'm going to construct a new number. This new number will have the decimal point, and what I'm going to do is I'm going to start with x, and I'm going to put this position here. I'll put this number, then I'm going to put this number. Then I'm going to put this number, then I'll put this number, which is an O again. Then put this number, which is O, and now the sequence goes to O to infinity, so I can quit doing that. Over here, I start with x again, and I can put the 2, then I put the 1 from here. Then I put the 1 from here, then I put the 5 from here, then the 5 from here, then the, let's see, I've got a 1 and a 5, and now another 1, this one here. Now I have to put the 6 from here, 3 from here, and I keep alternating back and forth. When I finish, I have one real number. That's incredible. Now, it doesn't have very smooth properties, which means that nearness over here may not be nearness here. So metrically, it's not smooth. But this shows you that infinity is quite a rich subject, and that we can talk about different kinds of infinity. And it just kind of enriches your knowledge to know that this is a different infinity, much larger for the functions than the real numbers, and the real numbers are much larger than the rationals or the integers.